This is the lesson video for 3.8 and 3.9. We will be doing this in class, but if you're working ahead or you will be gone, you can use that assisted note sheet and follow along. The note sheet won't look exactly like the video, but it will go in that order and have all the material. The video itself will have more screens and slides. You can see our goals. We're going to start talking about points inside or outside of a triangle that are considered the center of a triangle. So we have some vocabulary to talk about, how to make the constructions, and then what the relationships are that govern these. So we have to first talk about concurrent lines, because the sections are about points of concurrency. So anytime you have multiple lines intersecting at the same point, you have concurrent lines. So an asterisk that we draw is a set of concurrent segments. So multiple lines intersecting at the same point. So in the diagram I've got, you may want to sketch yourself one on your sheet. I have a set of concurrent lines. They are concurrent because they meet at that one intersection point. The lines themselves then are concurrent. So parallel lines are not concurrent. The point of concurrency then is that individual point, that one location where all the lines come together. So the first thing we're going to talk is some vocab about specific points of concurrency that happen by construction. So if I were to make all three perpendicular bisectors of a triangle by construction, the point that I would form is called the circumcenter. So the circumcenter is the name of this individual point that's formed when those three perpendicular bisectors of the three sides of a triangle come together. All triangles do this. This is not unique for certain triangles. The perpendicular bisectors of the sides of a triangle will be concurrent and meet. So as we look at relationships, we know some things about perpendicular bisectors from a past conjecture. If a point is on a perpendicular bisector, it's equidistant from the endpoints of the segment the perpendicular bisector interacted with. What that means is for segment AB, every single point on this perpendicular bisector is equidistant from AB. So point O right now is equidistant from A and from B. But point O is also on the perpendicular bisector of side BC. So therefore O is equidistant from points B and C. I didn't put the third perpendicular bisector in for side AC because I already know where the point of concurrency is. So if I need to locate the circumcenter by construction, I don't need to construct all three. I really only need to construct two to locate that point where the third one would come through. So that also tells me that point O is equidistant from vertex A as it is from C. So since the circumcenter is on all three perpendicular bisectors, here's what we know. It should be equidistant from each of those endpoints. So it should be equidistant from all the vertices. Since it's on all three perpendicular bisectors, that point, that circumcenter, is equidistant from all three of those endpoints of the segments, all three vertices. So this is how geometry finds a point that's the same distance from three locations. What I'm able to do then is I should be able to take my compass when I construct this, and I should be able to start a circle that comes out and intersects at those three vertices at the same time. So by construction, that circle would be called the circumscribed circle, because it's going around or about, if you're a root word person, the entire triangle. So what our circumcenter does is, the circumcenter is the center of the circumscribed circle, or a circle that touches all three vertices, three separate locations, points at the same time. So in other words, it's the center point of a circle through all three vertices. And that has some implications for things like locating where you might put a Walmart. You might want it to be equidistant or very close to equidistant from 3 separate towns so that all towns could benefit from it. If we continue this and we start making angle bisectors and make a triangle and find all 3 of its angle bisectors, the point you would locate where those 3 angle bisectors would come together is called the incenter. And it's that point of concurrency where all the angle bisectors come together. And we're going to talk that same idea that you know some things about angle bisectors. A point on an angle bisector, for instance, point C in this diagram, is on the angle bisector for angle R. Therefore, point C is the same distance away from that side of angle R as it is from, and again, think perpendicular distance, that side of angle R at the same time. Any point on that angle bisector will be equidistant from sides of of angle R at the same time. But our point here that I constructed using 2 angle bisectors is the point where the 3rd angle bisector would come through. So the incenter is on all 3 angle bisectors of the triangle. And because of that, it's equidistant from all 3 sides, not all 3 vertices, as you can see. It's not equidistant from Q as it is from R as it is from P. It's equidistant from all 3 sides of the triangle. So this might be if we have 3 highways and we need to think about how we could find a place that would be equidistant to each of the highways being lines. So what we can do then is we can take a circle, and instead of being able to start from that center point and touch all 3 vertices at the same time, what I'm able to do is start from that center point, and that will be the center as soon as my smartboard wants to cooperate. That will allow me to inscribe a circle. That means I will be able to reach with one circle all 3 sides. So the sides of my triangle will be tangent to my circle. Okay, so the and so part, that incenter is the center of the inscribed circle, we could say. And this works for all triangles. And then what you might want to say, it's the center point and that they'll be tangent to all sides. That circle that I make. So the incenter is the center that allows us to make the inside or inscribed circle. The circumcenter is the center that allows us to make the circumscribed or outside circle. By construction, feel free to locate that point with just 2 of the angle bisectors or perpendicular bisectors. The problems in homework will talk about situations where you might want to sketch and you might want to figure out which center you need based on whether you need to be equidistant from 3 individual locations like points or 3 sides, straight paths. Flipping to the back, the orthocenter is the point of concurrency or point where 3 altitudes of a triangle will intersect each other. And they will always be concurrent. They will intersect. So in the diagram you have, I constructed the 3 altitudes, and where they intersect, then that individual point is called the orthocenter. The orthocenter has several uses. We don't dig into them enough in order to see them. So orthocenter for now will be definition and necessary information, but it won't serve as the beginning of a construction of things that you will be responsible for. But you could construct an orthocenter. You'd simply construct 2 of the altitudes of the sides of the triangle. The final one, and this is where 3.9 picks up, is if we constructed all 3 medians of a triangle. Median is that segment that goes from vertex to midpoint. So we're talking about SR in this picture being one of the medians, and we're talking about PT being the other one. if I had put the third one in, that point of concurrency would still have been C. So now we're talking about one that sounds like it's from outer space, the centroid. The centroid is that point of concurrency where the medians come together. So the centroid does two things. It's the center of gravity or mass for a triangle. And what that means is if I made the triangle out of something rigid like metal, I'd be able to hold up the triangle from a single point. So under meaning, it would be the point. Where a triangle could be balanced at one individual location. I could pick up my pencil and put your triangle on the tip of my pencil and balance it perfectly, or hold it up for a mobile, something that hangs above something, by one point, and that would be the centroid. The centroid does one other thing, however. Centroid's got two really helpful relationships. So when you have it printed on yours, it says the centroid splits each median into two parts. So I can see right here that this is the centroid, just blew it up bigger, and it splits my median here into two parts. It splits the red median into two parts, and it splits the top to bottom median into two parts. They are not congruent parts. So if I were to check distances with my compass, what I would find is that whatever the part from the midpoint of the side to that centroid is, that centroid up to the opposite vertex is twice as long. So in that line, it says the distance from the centroid to the vertex is twice as long as the distance from the centroid to the midpoint of the opposite side. So we're going to try this relationship out. You have the same diagram. You can ignore the later stuff. So on this diagram, they give us information and they want us to find side lengths based on the fact that in their picture, they demonstrate that M is a midpoint, therefore M to Q is a median. They demonstrate that K is a midpoint, so therefore K to R is a median. They demonstrate that L is a midpoint, so L to P is a median, so C is that centroid point. It's where the medians are coming together. And what we know is it splits that median, each of those medians, in a 2-to-1 ratio. So as they tell me information about this, they'd like me to find individual values about this. So let's just start with the simplest. They told me that KC is 7. And KC is the part from midpoint to centroid, so that's the one part piece of this. So C to R will be 2 of those 7 pieces long, or 14. So when they ask us for the length for CR, that's the twice as long part, so it'll be 14 units long. The next thing they give us, though, is PL is 24 long. They don't tell us, with PL being 24 long, which piece is PC and which piece is PL. So what we're going to do is think about that this is supposed to be from C to L one length, and then that length is supposed to get repeated twice on the segment from P to C. So what I want to do is split that 24 into 3 equal lengths. Each would be 8. One of the lengths is here, and the next two 8s are here and here, making PC 16 long and CL 8 long. And finally, they tell me that QC is 10, and QC is the part from vertex to centroid. We can't go on the idea that it looks longer. We really need to know that it's that particular one. So that actually means that that's a 2-part length, meaning CM is one of those 2 parts, or 5 long. But the question actually asks us for QM, so QM is our 10 plus our 5, 15 long. As you work on the material for 3.8 and 3.9, please make sure that you refer back to this, check the reading in the sections, and ask questions as you go.